your next problem. Find the other 5 given 1. And again, reminder, given that the tangent is root 3 over 3, you could draw your little triangle. Tangent is opposite over adjacent. Label your opposite side as root 3. Label your adjacent side as 3. Do Pythagorean theorem, find your third side. And then you've got all the others. You've got sine alpha, cosine alpha, secant, cosecant, and cotangent of alpha. But let's try to do it with identities. Those identities I showed you yesterday. Well, actually, we can't this one. A lot of people are going to try to use that first identity and say, oh, the tangent is cosine over sine, so the cosine is root 3. The sine is root 3 and the cosine is 3. Can't do it. Should be obvious, actually, that, well, number one, sine can't be root 3. Because we said sine can never be bigger than 1. Cosine can't be positive 3, because, again, cosine can't be bigger than 1. There's other identities that you could use, actually other Pythagorean, what's called Pythagorean identities that you could use to solve this one. I haven't given those to you yet, so let's do it the other way. And then we'll talk later on about those other identities. Tangent of alpha, which is opposite over adjacent, is root 3 over 3. Pythagorean theorem, a squared plus b squared. What's the square root of 3 squared? 3 equals c squared. So c will be the square root of 12, which will be square root of 4 times square root of 3. There you go. This is actually probably the easiest way of doing it anyway. So therefore, the sine of alpha, opposite over hypotenuse, is root 3 over 2 root 3. You can divide radicals. Root 3 divided by root 3 is 1. So you're left with 1/2. The cosine of alpha. Now from there, if you'd like to, I don't know why you would, because you got your triangle. From there, if you wanted to use your Pythagorean, use your identities up here, you could. Cosine of alpha is adjacent over hypotenuse, which would be 3 over 2 root 3. We multiply top and bottom by root 3. So on top you have now 3 root 3. On bottom you have 2 times root 3, which would be 6, which is root 3 over 2. So that's sine, cosine. We already have tangent. So to find the other ones, we're just reciprocating. Sine and cosecant are reciprocals. If sine is 1/2, then cosecant is 2. Cosine and secant are reciprocals. I would reciprocate, look, cosine is root 3 over 2. If we reciprocate that, if you reciprocate this, you're going to have a radical on bottom. So what you can do, well, this was equal to this, and it was equal to this as well. Why not just reciprocate this? Okay, that way you don't have to rationalize. So instead of 3 over 2 root 3, you'll have 2 root 3 over 3. And then cotangent. Since tangent was root 3 over 3, cotangent would be 3 over root 3. Multiply top and bottom by root 3. That gives me 3 root 3 over 3, which reduces to just root 3. Next one, the secant is 4. So we can actually, now that we're given secant, we can go straight to, not cosine. Yeah, that's right. Cosine alpha. If the secant is 4, the cosine is 1/4. And then I'm going to draw my, actually let's do this one without the triangle. We can do it. I know that sine squared from my identities up here, sine squared plus cosine squared equals 1. And I'm given cosine. So I've got sine squared plus 1/4 squared equals 1. The more you work of these, the quicker you get at them. I've got to move 1/16 over, so now I have sine squared equals 15/16, because 1 whole is 16/16. To get rid of a square, I square root. So now I have the sine of alpha is the square root of 15, doesn't simplify, over the square root of 16. So the square root of 15 over 4. And if sine is the square root of 15 over 4, then we now have cosecant as well. which would be 4 over root 15, or 4 root 15 over 15. And now that I have sine and cosine, reminder that to find tangent, you can simply do sine over cosine. Sine divided by cosine will give you the tangent. So to find tangent, it's going to be sine, what is it going to be? Just root 15, good. It'll be root 15 over 4 over 1 over 4. The bottoms, if you do it correctly, guys, sine and cosine, the bottoms, if they're fractions, the bottom should always be the same. Okay? And when you go to divide these two things, they're always going to cancel. Leaves you with root 15 over 1 or just root 15 is the tangent. So therefore the cotangent, which would be the reciprocal of that, would be 1 over root 15 or root 15 over 15. Some common sine, cosine, and tangent values. Before we go into this, we need to go back and revisit from geometry basic 45, 45, 90 right triangles, and here in a second 30, 60, 90 right triangles. If you don't remember, shortcut-wise, anytime you have a 45, 45, 90 right triangle, since the two angles are the same, that makes this an isosceles triangle. And if the two angles are the same, then the two side lengths are going to be the same as well. If you got a side length of 1, the other side length is going to be 1 as well. The other leg. You got 2 legs and a hypotenuse. From this point, you could use Pythagorean theorem if you wanted to. It's pointless. The shortcut says to go from leg to hypotenuse, you will always multiply by root 2. So if your legs are 1 and 1, then your hypotenuse would be 1 root 2. If your legs are 3 and 3, your hypotenuse would be 3 root 2. If your legs were 4 and 4, your hypotenuse would be 4 root 2. You don't have to know this for what we're going to be doing today. But if you ever, ACT-wise or something else, if you ever have to go from hypotenuse back to a leg, let's say that your hypotenuse is 6. Then to go back to a leg, well, to go from here to here, we multiply by root 2. So to go from hypotenuse back to leg, you would divide by root 2. So that'd be 6 divided by root 2, and that's what we just did. You can't divide a number by a radical, so therefore you would rationalize. Multiply top and bottom by root 2, that'd be 6 root 2 over 2, or 3 root 2. If you ever have to go from hypotenuse back to leg. Now 30, 60, 90s. In a 30, 60, 90, everything revolves around the short side. And by the way, remember, short side will always be across from short angle or small angle. To go from short side to hypotenuse, you always multiply by 2. You always double it. So if you're given hypotenuse, you need to go back to short side, then you would have to. If the hypotenuse was 6, the short side is 3. If the hypotenuse is 8, the short side is 4. Also, to go from short side to longer leg or medium side, whatever you want to call it, to go from here to here, you'll multiply by root 3. So, you got a 30, 60, 90. Let's say that short side's 5, everything revolves around that. Hypotenuse is 10, medium side 5 root 3. 6, 12, and 6 root 3. 7, 14, 7 root 3. 8, 16, 8 root 3. Everybody see the relationship? Same way with 45, 45, 90s. If you're ever given the medium side and need to go back to the short side, you would divide by root 3 and rationalize just the same we did last ones. So now let's use those. And you've already got a chart. We copied down a chart the other day that had all these on it, so if you don't want to copy it, this is your chart. And this is where your chart comes from. Sine of 30. Let's go to our 30, 60, 90 right triangle and base it off of this. Here's my 30. If I don't know what the sine of 30 is, sine is opposite over hypotenuse. The sine of 30 will always be half. 1 over 2. Because again, in a 30, 60, 90, the hypotenuse is always double. So whether it be a 1 and a 2 or whether it be a 4 and an 8, it always reduces to a half. Sine of 45, we're going to have to go to the top triangle for this one. Sine of 45, opposite over hypotenuse would be 1 over root 2. When you rationalize it, you're going to get root 2 over 2. Sine of 45 will always be root 2 over 2. The sine of 60. Now we're going down to the bottom one. again. Sine of 60 would be opposite over hypotenuse would be root 3 over 2. Sine of 90 and the sine of 0. Here's the thing, you can't, you don't have a triangle to match that. Because sine is opposite over hypotenuse. Well, how in the world are you going to do opposite over hypotenuse if this is a 0 degrees? Think about what happens though. If this approached 0, now we're getting into some limits now. As this gets smaller and smaller and smaller, do you see that your opposite side would get smaller and smaller and smaller? As this approaches 0, this approaches 0, so opposite over hypotenuse would always approach 0 as well. The sine of 0 degrees is 0. As this gets closer and closer to 90, and you could look at either one to do this. As these angles get closer and closer to 90, the opposite side gets closer and closer to the length of the hypotenuse. So the sine of 90 is actually 1. If you could actually approach, if you could actually ever get to 90 degrees, you can, not that triangle. The hypotenuse and opposite side would be the same. Sine of 90 is 1. So there's, again, that's the values from your chart. Cosine of 0, okay, well, let's skip that and go down to cosine of 30. Cosine is adjacent over hypotenuse. Well, do you see the relationship now between sine and cosine? Well, is the cosine of 30 not the exact same thing as the sine of 60? Because the sine of 60, you're talking about opposite over hypotenuse. Is that not the same thing as adjacent over hypotenuse down here? So therefore, the cosine of 30 would be root 3 over 2. Cosine of 45, well, look, opposite over hypotenuse, adjacent over hypotenuse is the same thing. Cosine of 45, root 2 over 2. Cosine of 60 is the same thing as the sine of 30 is a half. And you see the pattern. Cosine of 0 will be 1. Cosine of 90 degrees will be 0. Tangents. The tangent, let's start with 30 degrees. The tangent of 30, here's my 30. Tangent is opposite over adjacent, which would be 1 over root 3. And when you rationalize that, that would be root 3 over 3. Tangent of 45, there's your 45 degree angle up here. Tangent's opposite over adjacent would be 1. Tangent of 60, opposite over adjacent would be root 3 on the bottom. Tangent of 90 is actually undefined. Because think about what we said a while ago about the opposite side. As you approach 90, that opposite side approaches 1 whole, but the adjacent side would be shrinking and would actually approach 0. And anytime you have 1 whole over 0, you can't have a 0 on the bottom. It's undefined. So therefore, the tangent of 0, 0. Now let me show you the easy way of remembering tangent. Tangent correlates to slope. Tangent, slope. The easy one to recognize here, if you're talking about slope, slope is rise over run. So if you're talking about the tangent of an angle, look at this 45. If you're talking about this angle here, it's rise and it's run. Well, to get from this point to this point, don't you rise 1? Same thing as over here, rise 1, run 1. Because tangent, is it not opposite over adjacent? Is that not the same thing as what slope is? Rise over run, opposite over adjacent, same, identical, same thing. Same here. If you want to find the tangent of 30 degrees, well, what's from this point to this point, what's the rise of that slant? It rises 1 and it runs root 3. Tangent and slope is the exact same thing. So anytime you want to find the tangent of an angle, just keep in mind that you're finding the slant of that angle. You're finding the slope of that angle. Okay? The measure of an angle. Now, up to this point, we talked about only angles from 0 to 90 degrees. We've dealt with right triangles. We're about to extend trigonometry to other angles. Angles beyond 90 degrees. And we need to focus on what am I talking about when I'm discussing a 300 degree angle? Well, what does it even look like? We're going to be graphing angles, and that's where we're starting here. The measure of an angle, angles bigger than 90 degrees and smaller than 0 degrees. These angles that we're going to be graphing, we're always going to put, it's called the initial side. When we're graphing them, our initial side is going to be along the positive x-axis. And we're going to rotate from there. Like in this case here, it looks like that's a 45-degree angle. We start with our initial side, and anytime you see the word initial, that's like a starting point. And then we're going to rotate up to the terminal side. And when I say terminal, I think terminate. Terminal side is where your angle terminates. So if we're starting here and we rotate up, it's going to terminate here. That's about a 45-degree angle. That's what the graph's going to look like. Our vertex will always be at the origin. But these are in what's called standard position. Standard position, the initial side's along the positive x-axis, the terminal side rotates up or down. Here in a second, we're going to actually rotate down as well. Here you see several angles in standard position. A 30-degree angle, a 45-degree angle, a 60-degree angle, a 90-degree angle. You don't have to write these down. Now in a second, you're going to be talking about what quadrant an angle lies in, and we know our quadrants, right? Quadrants start with quadrant 1 in the top right-hand corner, and they rotate counterclockwise, quadrant 2, 3, and 4. These angles here, they're going to be very special to you before very long. These are all the sine, cosines, and tangents that you're actually going to memorize. You're going to know what the sine of 225 degrees is. You're going to know the cosine of 300, the tangent of 330. We're going to memorize each and every one of these. Okay? You've already got some of them memorized. You've already got this quadrant memorized. Or maybe not memorized. You've got them written down. Before long, if I say, what's the sine of 30? Now, if we didn't know that, could I sketch out my 30, 60, 90, opposite over hypotenuse? Yeah, you could. I don't want you to have to do that. Sine of 30 is a half. Cosine of 45 is root 2 over 2. Sine of 60 is root 3 over 2. Cosine of 90 is 0. We're going to get to where we can pop these off pretty quick. And not only those, but if we know these pretty well, I promise these other ones are going to be extremely easy too. Okay? So moving on. Coterminal angles. What's co mean? Together, with, or together. Terminal, we just talked about that, right? Terminal side is where your it's where your angle ends, I guess you could say. Like this first angle here is a 50-degree angle. It starts with your initial side at the x-axis and it rotates up 50 degrees. These other two angles that are next to it are coterminal angles with 50 degrees. If I jump up and dunk a basketball, I'll probably hurt myself. But if I jumped up and dunked a basketball, I'm facing the basket. If I jump up and do a 360, why do they call it a 360? Because you rotated 360 total degrees. Is math. You rotated 360 total degrees, done. You ended up in the same place. 0 and 360, since you ended up in the same place, are coterminal angles. Now, if you're anything like me, I could actually do 1080s back in the day, which means I could jump up and I could spin around 3 times and then dunk. At a 1080, right, that's 3 complete revolutions. So I just gave you a revelation by explaining my revolutions. A 1080, a 360, a 720, all of those are coterminal. Coterminal simply means they end up in the same spot. So how do I find coterminal degree or coterminal angles? Easy, extremely easy. 50 degrees and 410 degrees are coterminal. Why? Because it's just got an extra rotation tacked onto it. This one rotated 50. This one rotated 50 plus another 360. This one rotated 50 plus 2 more 360s. They all 3 ended up in the same spot. Coterminal angles just have extra revolutions tacked onto it. Here you see your first glimpse of a negative angle. This one started at your x-axis and it rotated in the opposite direction. This is a negative 100 degrees. It rotated past, this is 90, right? We all know that the x and y axis form 90-degree angles. It rotated 10 degrees past that y-axis to give you negative 100 degrees. Now, you could tack 360 onto that. You could take negative 100, rotate it an extra 360 degrees, and look what's happened. Negative 100 plus 360 gives you 260. If you start at the x-axis and rotate 260 degrees, that's 90, 180, plus another 80 gives you 260, which ends up in the exact same spot. Those are coterminal. Or we could have went the opposite direction and took 360 away from it. So if you take 360 away, that's a negative 360 plus a negative 100, which gives you negative 460. So, to make a long story short, to find coterminal angles, either add a rotation on or take a rotation away. And you end up in the same place. So, find two positive and two negative coterminal angles with negative 50 degrees. So somebody take your calculator out or do it in your head. Let's tack on a rotation. What do you get? 310 degrees is your first coterminal angle. And you can check that. Negative 50, what quadrant does negative 50 end up stopping in? Fourth. It's about right there, right? There's negative 50 degrees. Now, 310, what you actually did there was went 90, 180, 270, plus another 40 degrees. You ended up in the same place. Another positive one, to get another positive one, you just tack on another 360, and you end up getting 670. So two positive coterminal angles with negative 50 would be 310 and 670, which would look identical. You just have another loop on it. You spun it another time, and that's how we show. That's how we draw 670 degrees. I would say, okay, here's 360, 670. Okay, you just show that you spun around once and then you went 310 more degrees. Now we also need two negatives, so the way you would find that is take your negative 50 and take away 360, which is negative 410, good. And then take away another 360 and you get negative 770. Those four angles are coterminal. Two positives, two negatives. Determine whether these are coterminal. Same thing. You have a 190 degree angle. Take 360 from that. What do you get? Take 190, take away 360, you end up with negative 170. Are those coterminal? Yeah. Take 150. Here, we'll do this one together. Take 150, add 360 to it. You get 510. Too low. Add another 360 to it, you get 870. Close, but are they coterminal? No. If you tacked on another 360, it's going to be way too big. So A is coterminal, and B, those two are not. Naming quadrants. We did that a while ago. Here's an extra practice. Start with your x-axis. 0 degrees, 90 degrees, 180, 270, 360. Okay, so 230. That's 90, 180, and this is 270. So do you see it lies somewhere in here? So 230 degrees would be somewhere in the third quadrant. It would actually be 50 degrees past your x-axis and 40 degrees before you get to your y-axis. So it'd be a little bit closer to the y-axis than x-axis. What quadrant is negative 580 in? Okay, here's my advice for you. Every angle lies in the same spot as its coterminal angles. So what I would do is take out my calculator. Negative 580, because I really don't want to do all those rotations, so I just do negative 580 and add on 360. Because, again, every angle is going to be in the same spot as its coterminal angle. Oops, let's try that again. Negative 580 plus 360 gives you negative 220. I still don't like that. Let's add another rotation. So negative 580 is the same thing as 140 degrees. Same spot. What angle, or excuse me, what quadrant? Second quadrant. It's between 90 and 180. Let me show you a trick here while we're on this. If you've got a negative 2,360 degree angle, and you want to add rotations on that to find coterminal, instead of having to do it plus 360, plus 360, plus 360, plus 360, if you'll hit enter and get that stored in there, and then do your answer plus 360, all calculators do this, right? Enter, 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 enter. That's 160 degrees. That way you don't have to keep typing in plus 360, plus 360, plus 360, okay? Get it stored in your calculator, hit answer plus 360, and then it continues doing the previous answer plus 360. It keeps doing those iterations, okay? 1380, I can use my trick on that one. Oops. So you have a 1380-degree angle, enter. We want to know what quadrant that's in, so let's start taking away 360s. Same thing as a 300-degree angle. So therefore it's in the fourth. Because 300 degrees, again, 90, 180, 270, 360. And what was it, 300? So that'll be somewhere right in there. 1380, that'll be 360, 720, 1380. So you have 2 full rotations and a partial rotation. No? You have 3 rotations, yeah. 1, 2. I should have went around again, shouldn't I? Should have been that. Okay. Because a 1080, we all know because we're all snowboarding fans. A 1080 is a triple rotation. Degrees, minutes, seconds. Degrees, minutes, seconds. The most used spot, or the most used application that I found for degrees, minutes, seconds is with like GPS location, GPS navigation, and all that. They use to find precise points on the map. They use this degree, minutes, seconds. Now, what we're going to do here, you have two different scenarios. Sometimes, and most of the time that you've dealt with, 28.37 degrees. You've done that, right? But think of it like this. Think of taking that and turn it into what's called degree, minutes, seconds. You see here a protractor zoomed in. And what you've got here is this arrow is pointing at, here's 40 to 50, so that's 41, 42, 43. That's 43 degrees and then some. Imagine if you took each of these between the degrees and you divided it into 60 more little slots. And okay, this is 40, what did I say, 43 degrees? And then you got 60 more slots. Well, exactly where are we? Out of those little 60 slots, now where are we? Okay, how many pieces do I go over then? And let's say it's about halfway, right? So about, if there's 60 little divisions here, I went over to about 30 of them. Well, what if it's not quite 30? It's somewhere between 29 and 30. And you took and divided that into 60 small slots. Okay, that's what degrees, minutes, and seconds are. Or you can think of it as like a fine-tuning knob. If you got one knob that tunes to, okay, this many degrees, and then I want to fine-tune that a little beyond 50 degrees. I've got this minute knob, and that minute knob fine-tunes it between 50 and 51 degrees. And then you've got this this second knob that fine-tunes it beyond that, okay, a little bit more precise. And that's what degrees, minutes, seconds are. To where, y'all recognize that picture? Okay. To where our location, now 34 degrees north, 85 degrees west. Would that get us to the school? No. It'd probably get us to the community, maybe Northeast Alabama. But once you threw in 34 minutes and 58 minutes, well, that might get us to the actual city. And then once you throw in those seconds, that pinpoints it even more and shows us exactly where we're at. Okay. I guess you could think of it as being a big area, and then a smaller area, and then an even smaller area. Fine-tuning. So, how do we go? And that is actually precise. You can go to MapQuest and type that in, and that's actually pretty close to this room. Not just the campus, but pretty close to the actual room. So how do I go between the two? You already know. That's what I showed you how to do the other day. Okay. I want to carry from 34 degrees, 37 minutes, and 22 seconds. Again, that's minutes and seconds. There are, and I don't know if you caught this a while ago, there are 60 minutes in a degree, and there's 60 seconds in a minute. Sounds familiar, correct? Same way the clock works. So if I wanted to change this to decimal form, well, I told you there's 60 minutes in a degree. How many seconds are in a degree? 3,600. 60 times 60. There's 3,600 seconds in a degree. So what I have here is 34 full degrees plus 37 sixtieths, okay, of another degree. plus 22, not 22/60ths. Be careful. That's the reason I ask you that. It's not another 22/60ths of a degree, but a 22/3600ths of a degree. Because there's 60 of these in a degree, there's 3600 of these in a degree. Type that into your calculator. You are now in decimal form. That's it. 34 full degrees, 37/60ths of another degree, and 22/3600ths of another degree gives us this. 34 full plus 37/60ths of another plus 22/3600ths of another. And honestly, I don't think you would have to put those. I don't know. You wouldn't. You wouldn't have to put those fractions or the parentheses in there because it knows the order of operation. It's going to divide before it actually adds. That gives you 34.6228 degrees. That's in decimal form.
How would you do that, David?
That's what we're fixing to do. You know how to do it, though. You don't realize it, but you know how to do it. I'm not going to work it again, but again, you would type this in as 86 plus 16/60ths plus 20 over 3600. Done. Okay, that's all you do to go from degrees, minutes, seconds to decimal. But how do we go? Good question. How do we go backwards? How do we go from this form back to degrees, minutes, seconds? Well, you got the first part. There are 44 full degrees. Does everybody understand that? It would be 44 degrees because those are full degrees. But this is a partial degree. You have 235 thousandths of another degree. So how many minutes is that? 235 thousandths of, let me write that down, 235 thousandths of a degree. Well, how many minutes is in a degree? 60. So that's 235 thousandths of a full 60 minutes worth of degrees. So what do? You do 0.235 times 60. And what do you get?
14.
There you go. 0.235 times 60 gives you 14.1. So now you have 44 degrees and 14 minutes. But you had another leftover, right? That was equal to 14.1, which meant 235 thousandths of that full 60 minutes gave you 14 minutes plus a remnant, plus a leftover. And what is that leftover? That is your seconds. So do we have 0.1 seconds? No. We have 0.1 of another minute. 14 full minutes and another 0.1 of a minute. 0.1 of a minute would be 0.1 of the 60 seconds, which would be how many seconds? 6. So 44.235 would be 44 degrees, 14 minutes, and 6 seconds. I will work another one of those for you. I do need to caution you. If there is ever a negative sign out front, drop the negative before you start working the problem. Makes it much easier. Drop the negative, and then at the end, go back and put the negative back onto it. Okay? If there's ever a negative in a problem, drop it to begin with, work the problem, and then go back and put the negative in at the end. It's going to save a lot of confusion along the way. I want to work another one of those. Let's make one up. 63.4875. Because I want to show you how quickly you can do this on your calculator. 63.4875. So that we know that's a full 63 degrees, so what you would do is take off the 63. You're left with a 0.4875. 63 full degrees. Take your 0.4875, multiply it by 60. Goodness. Try again. 0.4875. Which I know you wouldn't type that in. I was just putting it up there so I'd have it. 0.4875 times, there we go, 60 gives you 29 full minutes. And then you take that remnant, take off the 29, and you're left with a 0.25, or you can just type in 0.25. Multiply that by 60 again, and you have 15 seconds. So that would have been 63 degrees, 29 minutes, 15 seconds. Just take off the holes, take your decimal and multiply by your remnant times 60, your remnant times 60. Now, if I had 15.3 here, could I take that 0.3 multiply by 60 again? Yeah, I can get milliseconds. Okay. Nearly done, guys. Let's discuss radians, and then we're finished for the day. Angles up to this point have been measured in degrees. Today we start talking about another way to measure angles, which you're not going to use near as much. The only time you're going to use radians, a lot of times in your physics and stuff like that, you deal with formulas, and sometimes you can't plug degrees into formulas. Okay, but these radian measures, for some reason, they're much easier to plug into different formulas. So just another way of measuring angles. And this picture shows you what a radian is. If you took a radius, let's say that this is a radius of 2, and you took that radius and you stretched it along the diameter of along the circumference of your circle. You see that they've kind of done that there. You took that 2 and you kind of bent it along the circumference. The angle that is cut off by that arc is called a radian. And you would think, well, does it not matter? What if it's a bigger circle? Or what if it's a smaller circle? Does it matter? What if my circle was half that size? Let me do it in a different color. What if I had a circle about half that size? Would your radian not be different? Well, what now if you have a radius of 1? Well, doesn't that also make your circumference smaller? So now that radius of 1, do you see what happens? That radius of 1 would stretch to about right there. And is a radian angle the exact same thing no matter what size the circle is? Yeah. A radian is equal to right at 57.3 degrees. You don't have to know that. But that's just to give you kind of an idea of how big a radian is. A radian is about 57.3 degrees. Okay, now let's think. How do you find the circumference of a circle? Is it about pi times 9? So therefore, if this thing had, whatever. If you could take your diameter, half your diameter. Let's say the diameter is 2. We've got a diameter of 2 here. So what's the circumference? 2 pi, right? What's the radius? 1. Think about this circle. So your diameter, your distance all the way around is 2 pi. That's with a radius of 1. So therefore, what would that radian measure be? Because I told you a radian measure is you took whatever you're cutting off here. Okay, if this is a radius of 1, this is a radian measure. So anytime, and I know that came out really confusing. Anytime you're talking about a full circle's angle, that's going to equal to 2 pi radians. Or in simpler terms, here's what you need to know. 1 radian is half a circle. 1 radian, hang on. Rewind that. That's a mistake. There we go. Pi radians is half a circle. Yeah, change that in your notes. That was a typo. 100 degrees or 180 degrees is equal to pi radians. 360 degrees, a full rotation, would be 2 pi radians. So I kind of wanted to show you the connection. I did a very poor job of it there. To show you the connection between pi, why this pi is thrown in so much when we're talking about radians, pi and this radians. 2 pi radians is a full rotation. The same way as if you had a radius of 1, 2 pi would be the circumference. Well, 2 pi radians is the pretty much circumference or the angle around the entire circle. Again, to make a long story short, anytime you have pi radians, that's equal to 180 degrees. Pi, 180, same thing. So this is what a lot of times your radian measure is going to look like. We'll work 1 or 2 of these and stop. Your radian measures are going to be like 7 pi over 6. And notice there's no degrees up there. 7 pi over 6. Let me show you the easy way of changing these to degrees. Because most of the time, if I see radians, unless I'm plugging it into a formula, I'm going to change it over to degrees because I like working with degrees because it's what we've done our whole life. If pi is 180 degrees, somebody tell me what's pi over 3? How many degrees is that? 60. 180 divided by 3 is 60. What's pi over 2? That's 180. Divided by 2 is 90. So pi over 2 radians is 90 degrees. What's pi over 6? 30. Does everybody understand where those are coming from? Pi radians is 180 degrees. If you want to change those back to degrees, just plug in 180 for pi. So this is 60, 90, and 30. Well, look at this. 7 pi over 6. What's pi over 6? So what is 7 of those? That's it. So pi divided by 6 is, just take that part off. Pi divided by 6 is 30. 7 30s is 210. 7 pi over 6 is 200 degrees, or 210 degrees. Let's work some more of those. 5 pi over 3. The way I work that, pi over 3 is 60. 5 of those would be 300 degrees. 7 pi over 4. Pi over 4, erase that. Pi over 4 is, that's hard to divide, isn't it? It's one that you'll get used to. Pi divided by 4. Divide by 2 and divide by 2 again. Divide by 2, you get 90. Divide by 2 again, you get 45. 7 45s, 315 degrees. All of these that you just saw are common angles that you're shortly going to find the sine, cosine, and tangent of.